Hello everyone, and welcome to episode 2 of AAC Process Diagnosis. In the previous episode, we started from raw materials and discussed how raw material indicators affect slurry behavior, green cake formation, cutting, autoclaving, and final product quality. In this episode, we move one step further into a more critical area, formula design. In AAC production, process engineers usually define a preliminary ratio of sand, fly ash, quicklime, cement, and gypsum based on raw material characteristics, production experience, green cake behavior, and final product quality after autoclaving. Formula design is not only about the proportion of each raw material or the water-to-material ratio. More importantly, it is a reaction balance system. It needs to consider raw material properties, the matching between gas generation and thickening, pre-curing hardening, and autoclaving reaction. In this episode, we will focus on two key parameters in formula design: water-to-material ratio and calcium-to-silicon ratio. When we talk about formula design, many people may first think of a fixed set of numbers. For example, how many kilograms of each raw material should be added? How much water should be added? How much quicklime should be used? And how much cement should be used? But in actual production, technical and production teams do not only look at these numbers. They pay more attention to the stability, matching performance, and economic efficiency after the formula is applied in production. In other words, the core of formula design is not simply batching accuracy. The real focus is to control the key influencing factors during the formula design stage, so that the formula can meet both production process requirements and product performance requirements. First, we need to establish a diagnosis chain. After formula design is completed, raw materials enter the batching stage. Batching determines slurry behavior. Then the slurry begins gas generation, thickening, and hardening, forming the green cake. Green cake stability determines cutting quality. Finally, it affects the autoclaving reaction and the quality of the finished product. This chain is very important. Many formula-related problems cannot be directly observed during batching. Instead, they appear in later process stages. For example, when the water-to-material ratio is too high, slurry flowability may look good during mixing. But during the pre-curing stage, the green cake may lack sufficient support and sink easily. Another example is a low calcium-to-silicon ratio. It may not show obvious abnormal signs during batching, but the pre-curing hardening speed may become slow, and the cutting time may be extended. Therefore, when analyzing formula problems, we should not only look at the proportion of a certain raw material. Instead, we should identify the abnormal point along this reaction chain and determine whether the main cause comes from raw materials, production operation, water-to-material ratio, or calcium-to-silicon ratio. Now, let's look at the water-to-material ratio. In simple terms, the water-to-material ratio refers to the ratio between the total water and the total dry materials in the slurry system. The water includes water in the original slurry, water in the recycled slurry, additional water added during casting, and water brought in during aluminum paste premixing. The water introduced through aluminum paste premixing is often negligible in formula calculation. However, the water used to prepare aluminum paste slurry at a certain ratio still needs to be included. The water-to-material ratio is the first key switch that determines slurry behavior. It directly affects slurry viscosity, flowability, bubble movement, large pore retention and distribution, pre-curing time, and final product issues such as watermarks and undercured areas. Generally speaking, sand-based AAC is less sensitive to the water-to-material ratio. If it is not close to the critical range, the impact is usually not obvious, unless the sand slurry is too fine or has low water absorption. Fly ash-based AAC is more sensitive to the water-to-material ratio. Once it exceeds the critical range, it may easily cause thickening with trapped gas, or settlement and collapse. When the water-to-material ratio is too high, the slurry spread value becomes higher than the design value. The discharge speed becomes faster, gas generation becomes faster, and the whole pre-curing process may appear relatively stable at first glance. However, several problems may occur. There may be more bubbling around the inserting pinholes. Bleeding may appear above the slurry near the mold frame. After gas generation, the green cake may sink or turn over at the edges. Pre-curing hardening may become slower. Cutting strength may be delayed. Bonding may become serious during separation. The final product may show coarse and uneven pores. The final product strength may also be lower. The problem caused by excessive water-to-material ratio is often not that the green cake cannot rise. The real issue is that it cannot stand stably. If these problems appear on site, we need to check whether the water-to-material ratio is too high, or whether the fineness and water demand of the original slurry have changed. If the water-to-material ratio is too low, the slurry spread value becomes lower than the design value. The discharge speed becomes slower, gas generation becomes slower, and the slurry expansion process may look relatively sluggish. Several problems may occur in this situation. The slurry viscosity becomes high. The gas expansion height may be insufficient. Gas may become trapped inside the green cake. Large pores may remain in the green cake matrix, mainly because the air is not fully released by vibration. The final product density may become higher. The product surface may peel, and the pore structure may become uneven. In other words, when the water-to-material ratio is too low, the problem is not that the slurry is too thin and cannot stand. The problem is that the slurry is too viscous. Gas cannot expand properly, and the slurry cannot spread evenly. But we should also note that these problems are not caused only by the water-to-material ratio. For example, gas generation quality is related to aluminum paste. The length of pre-curing time is related to quicklime dosage and available calcium oxide content. Slurry viscosity is related to sand slurry fineness and the properties of the sand itself. Next, let's talk about the calcium to silicon ratio. The calcium to silicon ratio does not mean simply adding up all calcium oxide and silicon dioxide contents from all raw materials and calculating a total ratio. Here, calcium oxide usually refers to the available calcium oxide tested in the laboratory and the calcium oxide in cement. Silicon dioxide usually refers to the active silicon dioxide in the sand slurry, rather than the total tested silicon dioxide. In practice, the active silicon dioxide is often estimated as around 40 to 50% of the tested silicon dioxide, together with the silicon dioxide in cement. The calcium to silicon ratio is not an isolated chemical concept. It is directly related to whether the AAC reaction system is reasonable. It affects early hardening speed, hydration and hydrothermal reaction efficiency, green cake strength, and reaction products after autoclaving. In AAC production, the final goal is to form stable hydrothermal reaction products so as to ensure product strength and long-term stability. Therefore, the significance of the calcium to silicon ratio is not simply whether there is more calcium or more silicon. It reflects whether the whole reaction basis is balanced. If the calcium to silicon ratio is too low, calcium materials are relatively insufficient, and several problems may occur. First, the hardening speed may become slow, and the pre-curing time may be extended. Second, early green cake strength may be insufficient, making it difficult to reach proper cutting strength. During autoclaving, the internal reaction heat of the green cake may be insufficient, pressure loss may become serious, and the final product strength may be at risk. However, the calcium to silicon ratio is not the higher, the better. If the calcium to silicon ratio is too high, calcium materials are relatively excessive, and this may create another set of problems. Thickening may become faster than gas generation, resulting in trapped gas. Autoclaving expansion may occur. Products may bond together, become more brittle, and show higher shrinkage. The calcium to silicon ratio is a key factor affecting hydration and hydrothermal reaction. It directly influences the formation of target products, such as stable tobermorite phases, and further affects final physical properties, including compressive strength, thermal conductivity, and shrinkage. When problems occur on site, we can try to trace the observed phenomenon back to formula design. If green cake settlement appears during pre-curing, it may be caused by a high water-to-material ratio, which leads to slow thickening and hardening. It may also be caused by a low calcium to silicon ratio, which slows hydration and hydrothermal reaction. Or it may be related to fine aluminum paste, which causes gas generation to occur too fast. If cutting hardness is low, possible causes include high water-to-material ratio, slow thickening and hardening, low calcium-to-silicon ratio, slow hydration and hydrothermal reaction, or low available calcium oxide in quicklime. If bonding and corner breakage occur during separation, the direct reason may be low cutting hardness. And low cutting hardness may be caused by high water-to-material ratio, low calcium-to-silicon ratio, low available calcium oxide in quicklime, or fast lime slaking speed. If large watermarks and low strength appear after autoclaving, the green cake may contain too much water. High water content in the green cake may be related to a high water-to-material ratio or abnormal drainage in the autoclave. When analyzing site problems, we need to follow the whole chain from formula design to quality and conduct reverse diagnosis at each key process control point. Let's summarize the key points of this episode. First, formula design determines slurry behavior, gas generation, thickening and hardening, green cake cutting quality, and finally affects autoclaving reaction and final product quality. Formula design is not simple batching. It is a complete reaction balance design. Second, the water-to-material ratio determines slurry flowability, the matching between gas generation and thickening, the uniformity of product pore structure, and the size of watermarks. Third, the calcium-to-silicon ratio determines the speed of hydration and hydrothermal reaction during the pre-curing stage, the autoclaving system, the formation of target products such as stable tobermorite phases, and the final physical properties of the product. A reasonable formula design is not simply a proportion of raw materials. It should ensure that gas generation and thickening are matched, hydration and hydrothermal reaction are matched with the production rhythm, and the final product after autoclaving matches the design target.